All right, so we left off, we did some examples in terms of the x-axis, and I wanted to do some in terms of the y-axis, and then I want to do number 19. So in 6.2, there's really two parts, where if you take a solid, if you slice it, you get slices. And if you find the area of each slice, you can integrate that along the x-axis or the y-axis to get the volume of the solid. In Calc 1, we focus on kind of the second part where we have this shape and we revolve it around an axis. So we're always going to get a circular cross-section. So that's where pi comes in. We did the plenty of examples in terms of the x-axis, and now I want to do an example in terms of the y-axis. So let's look at did we get to number 4? I don't think we did in this section. Number 4 is part of your written homework. And number 4 is a washer with respect to the y-axis. So do you guys see that? If I revolve this around the y-axis, I get a washer. So this is number 4 in 6.2. Did we get to this one? Yeah. Okay. I got to it in the other class, so. So I have this function y equals 1 over x. And I'm looking for this shaded region rotated about the y-axis. So I'm rotating it about the y-axis, so my cross sections that I take here, if I come over here and draw it, I have the y-axis. And each slab is going to look like a washer, and this is delta y. So the distance from my axis of rotation to my outsidemost function, what is the distance from my axis of rotation to the outside function? 2, right? It's a constant, 2. What is the distance between my axis of rotation to my insidemost function? 1 over y, right? Because I want it as a function of y. Hopefully by writing the axis of rotation and the differential dy, that will remind me that I mean this function as a function of y. So this distance is 1 over y. So if I solve for x, I get x equals 1 over y. So what is the area of a cross-section? Will be pi 2 squared minus pi 1 over y squared, right?
Can you just solve for y for x to get a distance of the inner circle?
Yes. This distance here represented by the distance between x equals 0 to this y value. And the y value would be when you solve for x. So this has to be a function of y. So now if I want to find volume, I'm going to integrate from 0 to 2. Oh, not 0, sorry. I need to find this point along the y-axis. So this point is going to be when x is 2. When x is 2, what is y? 1/2. So I'm going to integrate from 1/2 to 2 of pi 4 minus pi divided by y squared dy. And of course I can factor out that pi out front and have pi times the integral of 1/2 to 2 of 4 minus y to the negative 2 dy. I need to find this point. So this is when x equals 2. So y would equal 1 over 2. The point on the curve. This is at x equals 2. So when does x equal 2 intercept this line? So when x is 2, y would be 1/2. So do you guys see that in terms of the y-axis?
How do you get a top number?
This was given as 2.
Okay.
So this is rotated about the y-axis. So my slices need to be dy. So my function needs to be a function of y.
And
Question?
when you're looking for the upper bound and the lower bound,
Yes.
you mean you're looking, because I thought the upper bound and the lower bound are x values.
Only when you're rotating about the x-axis. You're rotating about the x-axis, you would need to find this point, which would be the lower bound on x, and this point would be x equals 2. But we're rotating this about the y-axis, so we're integrating along the y-axis. So we need to look on the bounds on the y-axis, which this would be y equals 1/2, the y equals 2. Question?
Other than because the instructions tell you to, is there any reason why you decide y-axis?
Because
instead of
it's being
x-axis?
rotated about the y-axis. So my slices are going to be circular in the y-axis. If I rotate something about the y-axis,
Okay. just
then my
because it says
slices
it's-
need to be circular.
Because it said
because it says it's being
Okay.
rotated about the y-axis. So let's look at one more example of this, rotated about the y-axis. That one's pretty straightforward.
Was that the answer to the last one?
Well, you would actually integrate it and plug in your upper bound and your lower bound because
Okay,
it wants
so,
a value.
So integrate the 4
Yep.
minus y to the negative 2
Yep.
dy. Okay.
And that's
We can,
elementary, right? Yeah, I'm
Um,
convinced you guys can do that. On the exam on Tuesday, I'm going to probably just have you set them up. I will test you independently. Here's an integral, integrate it.
you will be given a picture or something.
Maybe, maybe not. I might expect you to draw it. Right? So anything I expect you to draw, like a quadratic, shift it up or down, a line, possibly x squared or x cubed, but it'll be pretty straightforward, something you've seen before if I asked you to draw it.
Just real quick.
Okay.
This 1/, if you scroll back up a little bit,
Mm-hmm.
I understand that, I mean, I know where you're getting the inner part of the washer,
Yes?
because it's the leftmost.
Function?
Yes.
Yeah.
It's the leftmost part of that cross-section, essentially, right?
Yes.
Okay. But we're calling it 1/. Oh, it's just an equation solved
Yes.
for x.
Yes.
Got it.
That's what you'll always do. You'll take an equation and you'll solve for that in x so you have a function of y. If you look on some of the written homework, I'm integrating this along the y-axis. This is a good example, number 3. It says y is a function of x. The very first thing you should do is write this function as x is a function of y because you're integrating along the y-axis. Let's look at number 3. I think it's part of your written homework, so some of you might have already had a chance to do this. So this is a line that has a slope of -2 that goes through the y-intercept at 3. So you might be given this line, you might not. You might be given this graph, you might be expected to graph it, but should not be too difficult to graph. And I'm looking for what was the equation of the line? Y equals 3 minus 2x. And I'm looking for this shaded region, and it's rotated about the y-axis. So this is going to be a disk, right? When I rotate this about the y-axis. So if I take slices, if I come out here, I have this y-axis, and if I take a slice, I get a full disk. So this is my axis of rotation, the y-axis, and this is dy. So I want to find the distance from my axis of rotation to my outside function as a function of y. So I need to solve for x. If I do that, I have y minus 3 divided by minus 2 equals x. So here I have minus 1/2 y plus 3 over 2. Does everyone see that? I'm integrating along the y-axis.
Yeah, and then you just broke up, algebraically, you just broke out that, what?
I solve for x, right? And then this is my function of y. This has to be a function of y because I'm integrating along the y-axis delta y. I can't have an x in there. So now the volume is, well, because y divided by minus 2 is minus 1/2 y. Minus 3 divided by minus 2 would be a plus 3/2. You could leave it like this, but it's a little bit easier to integrate when you have a constant times y plus or minus a constant versus if you have this. You could also pull out the 1/2. So let me just set this up real quick. I'm going from 0 to 2 of minus 1/2 y plus 3/2 dy. I could also pull out the 1/2 and integrate from 0 to 2 of minus y plus 3 dy. Sorry.
That doesn't quite work. Is that first function squared? Is that just
You're right. Thank you. Yeah, I forgot what I was doing for a minute. So the area in terms of the y is going to be pi r squared, right? So I have pi times minus 1/2 y plus 3/2 squared. That's my area function. That's what I need to integrate. So my volume goes from 0 to 2 of pi minus 1/2 y plus 3/2 squared dy. So then you can square this out and get a polynomial and add like terms and integrate it. You could do a u substitution if you wanted to. There's multiple approaches to that. But what I'm going to focus on in this section is, can you set this up? Does that make sense? So what are my bounds on my y-axis? I'm going from 0 to 2. Right? If I sweep through and go from 0, I'm getting this slice. If I go to 2, I get this slice. So everything's kind of good there.
So the bounds are just, it's the interval on the rotational axis.
Yes.
So if it's the x, then it's those bounds.
Yes. And that's something that repetition really helps here when you say, okay, what does a slice look like? I'm going to draw that. If I have an axis of rotation, the y-axis, I'm going to draw the y-axis, and I'm going to draw that slice around the y-axis. And then I'm going to put dy. So I put y, dy. That's going to remind me that my bounds are on y, and my function needs to be a function of y. If my slices are along the x-axis, I draw the axis of rotation to be the x-axis, and I put x, and I put dx. That tells me my function is a function of x.
I don't want to be overly confusing by this reference, but I know from several chapters back there was a type of problem where we would intentionally, like right at the beginning, one of the methods to solve it was to literally just switch the places of the x and the y.
That was an inverse function.
Okay.
That's
And
totally
not
different.
at all
No.
related. Okay, good. So here, when we're trying to isolate the x, we're actually just algebraically solving for x.
Yes.
Okay.
Yes.
Okay.
You're just solving for x to get a function of y.
Yeah. Okay.
Okay, so the last one I want to do in this section is number 19. And number 19 is on your homework. And what number 19 says is you have a function bounded by the curve y equals x cubed. But the cross sections between, I think it's 0 and 1, 0 and 1, my cross sections in here are square. So if I try to draw this here, so I have a square shape. Didn't quite go to plan. There, if this is my shape, if I took a cross section, I have a square. I don't know, this is a little bit better drawing for some
Wouldn't
reason.
it have to be really far down on it?
What?
Wouldn't it have to be really far down on the graph, or would it be able to be up down?
So the perspective here is a little difficult to kind of draw because I have two dimensions. I'm trying to do a three-dimensional object in 2 dimensions. So this is the top of it. If I take slices down this, I have square.
Okay.
You guys see that? But it's bounded by this curve y equals x cubed. So let me just go in here and say if I take a slice, this slice is square, not circular. There's no rotation. So if I take a slice out here, it looks like this, and I have some thickness dy. So if I was to pull this out and lay it flat, I would have this shape. So your book does a decent job of showing this idea of a pyramid. That you can see that the cross sections are square.
Oh, yeah, okay.
Right? So that's exactly what we're doing here, except our shape is bounded by this curve.
So if we were looking at it from the top, is where we can see.
Yeah, if you look at it from the top, you see the square. And if you take slices of the square, they're getting smaller and smaller and smaller against this curve. So how do I find the area of a square? If this is the length of the side, what's the area of a square? S squared, right? S times S, which is S squared. So S would be this distance. What is the distance between the y-axis and the function in terms of y?
Cube root of y.
Yeah, so here this would be the cube root of y. So the area would be the cube root of y squared, which would be y to the 2 over 3. Right? There's no pi here because the slabs are not circular. The only reason why pi comes in because the area of a circle is pi r squared.
What is it? I mean, I think I get that this is square and everything, but I need to know, is it the function that tells us that it's not a rotational?
The
How
setup.
do we know when we approach this?
So
that
this
it's
is
not?
number 19. You won't have one like this on the exam. Because we're going to only focus on rotational in Calc 1. In Calc 2, you will do both types. So you see, find the volume of a solid whose base is the region bounded between y equals x cubed and the y-axis, from 0 to 1, whose cross sections are taken perpendicular to the y-axis are square.
Oh, so the problem itself just says right off the bat.
Yes, so
It's square.
I'm taking it perpendicular to the y-axis, and each slice is going to be square. So if I integrate from 0 to 1 of the y-axis, all I have to integrate is the area function. Right? So the area function is this. Right? So if I integrate from 0 to 1 of y to the 2 over 3 dy, I get y to the 5 over 3 divided by 5 over 3. Flip and multiply. Plug in 1. I get 3 over 5.
So it's the same exact method, you just don't have pi in there because the problem itself said this is square.
Correct.
Okay.
So you could see an example if I look at the line y equals x, and let's say I take cross sections that are square here.
It's still rotating around.
No, there's no rotation. There's no rotation here.
That's the thing is that's why they're telling us at the beginning that it's a square.
Yes, they're telling you that this is your solid. This is the top of your solid. If I take a cross section of this, I get a square. The squares are getting smaller and smaller. This is a square here. This is a square here.
So if it's not being rotated, why does it?
Because the area for a square is S times S.
So if it's a rectangle,
You would have, Yeah, this method, you would have to then know what are the bounds on the y-axis. And you would do a problem like that in Calc 3, where you integrate along the x-axis and you integrate along the y-axis, that's when you use volume. But yeah, in this case, it's a square. The area of a square is s times x. And the side length, since it's a square, the side length represents the distance from y to this function in terms of y. It's the exact same process. The process in 6.2 is find what a cross section looks like. So find the area of a cross section. When we did circles, we have pi r squared. And when we did the washer, we have pi the outside radius squared minus pi the inside radius squared. And then we find our bounds of integration. If we're integrating along the y-axis, we need functions of y, and we look at the y-axis for our bounds. If we're integrating along the x-axis, we look at the function in terms of x, and we integrate along the x-axis. The concept is the exact same. The application here, this is not a solid of revolution. This is just a solid, which the cross-sections turn out to be squares. If the cross-sections were triangles, you would then have to find the area of a triangle. And it would be potentially a function of x or a function of y. Because the triangles are changing. They're getting smaller or they're getting larger, depending on how you're integrating it.
Yeah, so generally speaking, you're going to be told, at least in the part where you're solving the problem, you'll either get like a three-dimensional picture that shows you what it is, and then from there you can infer what the cross-section looks like.
Yeah, so
Or the
just,
problem itself will say the cross-section is this shape.
so like I've said in Calc 1, we're going to focus on solids of revolution.
You got it.
If you look at old final exams, which at this point you should be somewhat comfortable, if you go to the last two problems, it's either going to be a 6.1 or 6.2 problem. Let's see. I'm more familiar with this exam. So find the volume of a solid that is obtained when a region under the curve y equals the square root of x over the interval 1 to 4 is rotated about the x-axis. So this one's a pretty straightforward application. They actually want you to calculate it. So if I have y is the square root of x, and I'm finding 1 to 4 on the x-axis, so I'm going from 1 to 4. I'm rotating about the x-axis. So I'm looking for this volume. I draw a cross-sectional area. Since I'm rotating it about the x-axis, I draw my cross-section perpendicular to the x-axis. I draw my axis of rotation. My slice is perpendicular to the x-axis. So this is dx. The distance from the axis of rotation to the outside function is what? Square root of x. This is about as easy as it gets, right? What is the volume? Integral from 1 to 4 of pi x dx.
Well, it's pi. Right, okay.
Right, because this area is pi square root of x squared.
Right.
Does that make sense?
Should put that one on the line.
So integrating this is no problem at all, right? Sometimes it will say find the volume of a solid base whose region in the first quadrant bounded by, this is an example of what we used to test on. The cross sections perpendicular to the x-axis are square. But like I said, with snow days and some of the other instructors, they're not covering that part of 6.2. So you can see that was also in 2009. So.
Since 2009.
Sketch the region B in the first quadrant bounded by these two curves and set up the definite integral for the volume of a solid obtained by rotating B around the x-axis. Do not evaluate the integral. This would be one.
Rotating it around the x-axis would be
Yes.
circles.
Yes. Any rotation is going to be circular. right? So you guys should be comfortable with this. One thing, in the past I've graded this problem, and one thing that I see students struggle on is graphing x squared and x cubed on the same graph. So if I graph x squared, I look like, so this is x squared. X cubed looks like this. Y equals x squared, y equals x cubed. Between 0 and 1, x cubed is smaller than x squared, right? Because a half cubed is an eighth versus a half squared, which is a fourth, and an eighth is less than a fourth.
So and you can tell that by looking at the graph, because from going from left to right, the cubed function approaches the intersection from the bottom.
Yes.
Okay, that's good.
But assuming
I
you
don't-
know that in the first place.
Yeah, assuming you know how to graph it in the first place is the trick. Because I've seen students they know what x squared looks like, they know what x cubed looks like, but when they put them on top of each other, they don't know where they necessarily go in their intersection. So then if I rotate this about the x-axis, I'm going to have a washer, right? So I have this distance and this distance, right? So the upper function would be x squared, and my lower function would be x cubed. This is from a final exam, 2009 final exam. So yeah. Related rate. Yeah, x equals, oh, that's a different problem. Yeah, it's similar, except then you're really graphing the square root of x, which is a different function. Yeah, they still intersect at 1. I was expecting this one to be the x squared, y squared one. But yeah, this is a different problem. That's a good catch. I think maybe it was on 11. Sometimes they'll give you the graph. So this coordinator was nice in the fact they gave you the graph here. So we did an example like one of these. This is a function that's being rotated about the x-axis. So these slices are washers. So then you need to just know the distance from here, and the distance from here. Okay, so I want to give you guys plenty of time to take your quiz. Originally,